To understand why this disagreement is terrifying, we need to go back to a century-old yardstick, a new generation of instruments, and a number that wouldn't behave. The number that wouldn't behave, the Hubble tension. Start with the stakes. Two gold standard methods weigh the same universe and hand back different answers. Not close enough, not within error. Different. On one side, the late universe distance ladder, Cepheid variables pulsing in nearby galaxies, type Ia supernovae blazing like standard candles farther out. On the other, the baby echo of the cosmos, the cosmic microwave background, patterned by sound waves frozen when the universe was 380,000 years old. Both are precise. Both are careful, and they don't agree. From the latter's perspective, it's straightforward. You calibrate brightness. First, Cepheids, stars that brighten and dim with a steady rhythm. Their period tells you their true luminosity. You check that against parallax measurements, tiny apparent shifts in position as Earth orbits the Sun, so the 0 point isn't guesswork. Then you climb. Cepheids live in galaxies that later host type Ia supernovae. Those supernovae explode with a well-behaved peak brightness once you standardize them. Suddenly, you have yardsticks reaching deep into the late universe. Compare distances to redshifts, and you get a Hubble constant around 73 kilometers per second per megaparsec. It sounds clean. It wasn't. Dust can redden light, metallicity. The chemical richness of a star can tweak the Cepheid period, luminosity relation. Some teams argued that crowding in dense star fields made Cepheids look brighter than they are. So they ran audits, new filters in the infrared to cut through dust, sharper imaging with Hubble, and then Webb to separate stars that blur together, independent anchors like the tip of the red giant branch to cross-check the 0 point. Each time they knocked down a systematic, the number stayed high. The ladder kept landing near 73. Meanwhile, the early universe told a different story. The Planck satellite mapped the CMB in exquisite detail, reading the acoustic peaks, the ripples set by sound waves in the primordial plasma. Those peak positions depend on the sound horizon, the distance a pressure wave could travel before light decoupled from matter. Feed that physics-heavy snapshot into the standard cosmological model, matter density, dark energy, baryons, neutrinos, and you infer a Hubble constant around 67. The inference isn't a direct measurement, it's model-dependent, but the model has nailed a lot of other things, from element abundances to large-scale structure. Here's where it gets tangled. Parameters in the early universe fit are entangled. Change the assumed helium fraction or the number of relativistic species and the inferred expansion rate shifts. Priors matter. So teams pushed. Vary the model, widen the priors, let extra neutrino-like radiation in, relax assumptions about spatial curvature. Each test moved the needle a little, but the core result held up. The early universe inference stayed low. You can feel the tension in the room when results land. Latter proponents point to multiple independent rungs, Cepheids, red giant branch tips, masers in galaxy disks, strong lens time delays, even gravitational wave standard sirens beginning to weigh in. Early universe proponents counter with the internal consistency of the CMB and baryon acoustic oscillations that stitch the early and late universe together through the sound horizon. Both sides have citations. Both sides bring receipts. Then new eyes join the fight. The James Webb Space Telescope, with infrared vision and finer resolution, reobserved Cepheid fields that Hubble had charted. If crowding and dust were secretly biasing the latter, Webb should reveal it. Some teams saw Webb reinforce the higher H, once more near 73. Others, using alternative rungs like the red giant branch without Cepheids, landed closer to 70 and argued that within uncertainties the crisis softens. It didn't dissolve, it got sharper. Several groups now agree on this much. It's hard to push the ladder all the way down to 67 without inventing new problems. Meanwhile, gravitational lensing added drama. Time delays between multiple images of a single quasar let you solve for distances without standard candles. Those analyses, with careful modeling of the lens galaxies, have tended to favor higher H values, though their systematics, mass profiles, line-of-sight structure, are notorious. A multiply-image type Ia supernova, measured with Webb, offered a new route and also leaned high. The pattern is frustrating. Late universe, direct-ish methods are clustered high. Early universe, model-tuned inferences are clustered low. What nobody knew at the time, this wasn't just about one number. In parallel, a quieter debate over structure growth, how clumpy matter becomes over time, started to hum. Weak lensing surveys whispered that the universe might be slightly less clumpy than Planck's model predicts. Another small crack in the paint. Separate, connected. The arguments spilled into conferences and Slack channels. Here's the human part. Imagine months of calibration checks, blinking through star fields at 2 a.m., trying to decide whether a single Cepheid's profile is contaminated by a neighbor faintly bleeding into the pixel. A postdoc flags a metallicity correction that wasn't applied consistently in a subset. The team reruns the entire pipeline. The answer moves by 0.3. Not enough. The tension lives. Stakes again because they're the heartbeat. If the latter is right, the early universe model is missing something. A tweak around recombination, maybe energy that briefly flared and faded. If the early universe inference is right, then dozens of clever distance tricks are all biased in the same direction. Either way, our confidence in the rulebook takes a hit. This was the moment everything changed. New data didn't collapse the disagreement, it framed it. The universe wasn't going to hand us a neat compromise. While expansion fractured, another number began to whisper, one that controls the way light and matter talk. The fine structure constant's quiet drift. While the expansion rate argued in public, a softer rumor passed hand to hand. Alpha might be drifting. Not a dramatic lurch, just a quiet wobble in the fine structure constant, the number that tells you how strongly light couples to charged particles. Alpha lives inside every spectrum line, every chemical bond, every star's heart. Move it a hair and the universe breathes differently. That's why the whisper mattered. To chase it, astronomers turned quasars into time machines. Light leaves a quasar when the universe is young, threads through clouds of gas, and those atoms stamp the beam with absorption lines, thin notches at very specific wavelengths. If alpha in that ancient cloud was slightly different, the spacing between certain lines shifts. Compare the pattern to today's lab values and you read a tiny change across billions of years. The method that unlocked sensitivity was called the many-multiplet technique, and it did something clever. Instead of tracking one line, S-drift, it compared a whole family of transitions from different ions, each with a different sensitivity to alpha. By taking a weighted chorus instead of a solo, you amplify the signal. Here S where the field split. Early analyses using Keck in Hawaii and the VLT in Chile compiled hundreds of absorbers. The combined map didn't show a uniform drift, it hinted at a dipole, a directional pattern where alpha looked a touch higher in one hemisphere of the sky and a touch lower in the opposite. The amplitude, parts per million. The significance, intriguing, not decisive. The stakes, immense. A directional variation would mean the universe has a preferred axis baked into the constants themselves. But systematics lurk in every pixel. HL spectrographs can warp wavelengths across the detector. If your calibration lamp lines don't trace the same optical path as the quasar's light, tiny distortions masquerade as physics. Isotopes complicate things too. Absorption lines aren't single notes, they're chords from different isotopes. If ancient gas clouds had different isotope ratios than local lab samples, you could mistake chemistry for drifting alpha. Teams went back to basics. Laser comb calibrations to straighten the wavelength scale, cross-checks between instruments, explicit modeling of isotopic shifts for magnesium, silicon, iron. Conflicts sharpened. Some groups using ultra-stable laser comb, calibrated spectra, reported null results, no significant variation in alpha when they restricted to the cleanest systems. Others, reanalyzing larger catalogs with updated calibrations, saw the dipole pattern persist, nudging toward 3 to 4 sigma across the full sky, but softening when you slice by redshift or instrument. One team spent months building a pristine sample, only to throw out a dozen absorbers after finding a single arc lamp exposure had saturated and skewed a wavelength solution. That decision moved their result from a 2 sigma hint to a shrug. They published the shrug anyway. Meanwhile, Webb's infrared eyes entered the story. Quasar absorbers at higher redshift shift into wavelengths Hubble couldn't reach. With Webb's stability and resolution, you can target transitions less vulnerable to blends and atmospheric contamination. Early Webb spectra added leverage at the extreme end, redshifts 5 and beyond, where the many-multiplet method is starved of clean lines. The first trickle of results did what you'd expect from a cautious universe. They tightened constraints and kept the door cracked. No sweeping drift, but enough room left for a subtle anisotropy if the systematics are truly tamed. Why would alpha vary at all? Theorists dusted off scalar field models where what we call constants are values of fields rolling slowly through space and time. In some versions, the same field that drives dark energy couples weakly to electromagnetism. If that field isn't perfectly uniform, alpha inherits a map. That would link the Hubble tension's dark energy suspicion to the quasar whisper. Tempting, but dangerous. Any coupling strong enough to move alpha must also thread through laboratory tests, atomic clocks, equivalence principle experiments, the oclo-natural nuclear reactor's ancient isotope ratios. Those are tight fences. Most viable models have to tiptoe. The consequences, if real, aren't academic. Shift alpha by a few parts per million and nuclear resonances budge. Decay rates we use as clocks tick at slightly different speeds. In stars, opacities change, altering how they transport heat. Molecular energies shuffle, changing how clouds cool and collapse into stars and planets. Chemistry's periodic table wouldn't rewrite, but the margins would smear. Life's comfortable window depends on molecular coincidences encoded by alpha. The whisper touches biology by way of astrophysics. Back in the data trenches, the human moments keep the guardrails up. A graduate student, 3 years into a thesis, realizes a telluric correction, Earth's atmospheric absorption, was misapplied in a subset of VLT spectra. The fix erases a tempting outlier. A competing team, midnight in a Slack channel, shares raw calibration frames with rivals because the only way to kill a distortion is to replicate it. A principal investigator tells their group, if we find a variation we don't believe, we publish the non-detection and sleep well. Meanwhile, clocks on Earth quietly listen. Optical lattice clocks comparing frequency ratios, ytterbium against strontium, aluminum against mercury, set world-leading bounds on present-day drift in alpha. Year over year, they report changes smaller than parts in 1018. Those are direct, local tests, and so far they point to stability. If the quasar dipole is real, maybe it's spatial more than temporal, or maybe the coupling is environmental, stronger in pristine intergalactic gas than in our dense, screened laboratory. That's a specific prediction some scalar field models make. Screening hides variations where matter is thick. This was the moment everything changed for alpha. The field matured from did we see something to can we rule out our own favorite error? The answer so far is humility. The best we can say is that alpha doesn't scream, it whispers. And the whisper is directional enough, faint enough, and consequential enough to keep telescopes pointed at quasars and labs locking lasers to atoms. If light's coupling even wobbles, gravity's grip won't be far behind. G, the most annoying constant in physics. If alpha whispers, G mutters and contradicts itself. Isaac Newton's gravitational constant looks simple on paper, one number that sets how strongly masses pull. In the lab, it's a gremlin. Tiny shifts in G would tilt planets' orbits, reshape stars, and ripple through everything that falls. That's the stake. Gravity is the stage on which every other law performs, and the stagehands can't agree how heavy the scenery is. The classic way to weigh G is a torsion balance. two small masses on a bar suspended by a thin fiber, twisting ever so slightly toward larger masses nearby. You angle mirrors, bounce laser light, and red microradian twists like a seismograph for gravity. The signal is barely there, living in the space between air currents and the heartbeat of the building. Modern experiments bury these setups in basements, float tables on pneumatic legs, and chase thermal gradients with obsessive insulation. Still, the numbers disagree beyond their quoted errors. Meanwhile, a new generation tried a different trick: atom interferometers. Launch cold atoms upward in a fountain, split their matter waves, let gravity tug the paths out of phase and recombine. The interference fringes shift by an amount set by g when you move source masses around. It's gravity measured with quantum waves instead of twisting bars. Different systematic demons, same headache. When you line up results from torsion balances, atom interferometers, and pendulum variance, you see scatter that doesn't compress neatly into a single mean. The G paradox isn't that we don't know G. It's that our most careful methods disagree more than they say they should. Physicists built error budgets like crime scene boards. Thermal creep in fibers, microscopic changes in twist with temperature can mimic or mask signal. Seismic noise from distant traffic couples to the floor and then the fiber. Magnetic impurities in masses let minute fields tug where only gravity should. Even how you model the test masses, are they perfectly uniform, feeds uncertainty. In atom interferometers, wavefront aberrations, vibrations, and gravity gradients from nearby walls show up in the fringes. Labs tried blind analyses, swapping mass configurations without telling the analysts to see if expectations were biasing the fit. The spread narrowed. It didn't die. What would it mean if the spread were real? Planetary dynamics are a tight leash. You can't just crank G by 1% without Mercury telling on you. But the lab scatter is at the tens of parts per million level. Tiny, yet not nothing. At that scale, G shifts could tweak Earth's internal heat budget by changing how pressure and density trade off in the core models we use. In star formation, the threshold where gas clouds collapse versus stall depends on gravity's strength against thermal pressure. Move G and you move the line. In a universe that already struggles to form the smallest galaxies at the right times, that line matters. While basement labs wrestled with fibers and fountains, astronomers stared into a different gravity riddle. In spiral galaxies, stars far from the center orbit too fast if you only count visible matter. Lensing maps curve light more than starlight mass can explain. We call the extra pull dark matter, and the big picture model handles a lot. But the way gravity behaves on scales from labs to galaxies to the whole cosmos feels like a stack of rules glued together. Newton here, relativity there, dark matter on top, dark energy stretched across. If G were hiding a subtle environmental dependence, different effective strengths in different regimes, we'd be seeing only shadows of the deeper rule. There's a human moment here too. A team in Europe spends 18 months rebuilding a vacuum chamber around their torsion balance to chase a whisper of thermal drift. They switch to fused silica fibers to kill magnetic sensitivity. The new data lands a hair lower, tightening their uncertainty bars, widening the gap with a rival lab. They publish anyway, with a title that underscores the conflict rather than smudging it into a consensus. Across the ocean, an atom interferometry group runs nights with the building elevators locked to cut vibration, logging notes like pilots. One morning, their phase jumps by a fraction of a fringe when a delivery truck idles outside. They move the truck. The phase calms. The lesson sticks. Gravity is patient. Experiments must be more patient. The philosophical itch is hard to ignore. We treat G as a universal constant because it behaves that way in the equations that win. But the equations are effective, summaries of deeper behavior in certain limits. In some scalar tensor theories, the gravitational constant is really a field whose value can vary in time or respond to local matter density. Screening mechanisms hide variations in dense environments and reveal them in the thin intergalactic medium. If that's the game, then Lab G and Cosmic G are cousins, not clones. Most tests say any drift is tiny, but tiny is all it takes to stitch together anomalies that refuse to match. Here, S where this links back to the broader glitch. If alpha might be nudged by a dark field, and G might be effective rather than absolute, then the constants aren't Platonic numbers. They're settings the universe dials under conditions we don't fully map. The lab fights over G aren't a sideshow. They're a stress test for the idea that constant means constant. Out in the dark, on scales too big for wires and lasers, gravity keeps acting like it's missing a rulebook we keep trying to rewrite. The dark sector's two-headed monster. Out in the dark, gravity acts like it's missing a rulebook. 95% of the cosmic budget is booked under two line items we can't see: dark matter and dark energy. They're placeholders that behave like facts. One clumps, one pushes. Together, they keep the visible universe in its lane, most of the time. The first head showed itself in the 1970s when astronomers mapped how fast stars orbit in spiral galaxies. Far from the center where starlight thins, speed should drop. They didn't. The curve stayed flat. Later, gravitational lensing traced the same story in the way galaxy clusters bent background light. There was mass the stars couldn't account for, sitting like invisible scaffolding. You could tweak Newton's law or you could add missing mass. The field split, then the evidence piled up. The cosmic web of structure, the pattern of the CMB's acoustic peaks, all of it looked cleaner if you let cold, slow-moving dark matter seed galaxies and clusters. The second head arrived like a plot twist. In the late 1990s, two teams measuring distant Type Ia supernovae expected to see the universe's expansion decelerating under gravity. Instead, the light said expansion was speeding up. The simplest fix was a cosmological constant, energy inherent to space itself. Call it dark energy. It doesn't clump. It dilutes differently than matter. And once you add it to the equations, the supernovae, the CMB, and baryon acoustic oscillations line up into a model that fits nearly everything with 6 parameters. That model, lambda CDM, became the default rulebook. But default isn't destiny. The Hubble tension pressed its thumb on the scale, and the first suspect many reached for was dark energy's mood. If the lambda isn't a true constant, if it changes with time, then the sound horizon inferred from the early universe could shrink, lifting the CMB's inferred Hubble constant toward the latter's number. Early dark energy models tried exactly that, a field that turns on briefly around recombination, contributing a few % of the energy budget, then fades. The payoff is surgical. You touch the era that sets the acoustic ruler without wrecking late-time successes. That surgery leaves scars you can look for. Early dark energy changes the exact spacing and heights of the CMB's acoustic peaks. It tweaks how structure grows, shifting the amplitude we summarize as S8. If you're watching weak lensing surveys weigh the clumpiness of matter, you should see the ripple. Some analyses did hint at a slightly lower S8 than Planck prefers, which made early dark energy tempting. But push too hard and you break something else. The models that erase the Hubble tension cleanly often pull S8 the wrong way or demand extra relativistic species that other measurements constrain. The field lives in this narrow canyon where a small pulse might help without toppling the bridge. Meanwhile, dark matter itself refuses to sit still. On galactic scales, the way rotation curves rise and the tight relation between observed acceleration and baryonic mass, the radial acceleration relation, look almost too clean, as if gravity is being gently modified. In big clusters and in the CMB, invisible mass acts like particles. At small scales, pure cold dark matter predicts dense central cusps and too many satellites compared to some observations. Baryonic feedback, supernovae and black hole winds can reshape halos, but the bookkeeping is messy. Theories sprouted in the cracks: warm dark matter to smear out small structures, self-interacting dark matter to puff up cores, superfluid phases that mimic modified gravity inside galaxies while behaving like particles in clusters. Here's the connective tissue to our glitch. If the constants we trust are really parameters of fields, then the dark sector can carry those fields. A scalar that drives cosmic acceleration could couple tiny amounts to electromagnetism or to the strengths of forces in ways that are screened in dense environments. That would make alpha look directionally different in the thin intergalactic medium while keeping labs quiet. It would also make the effective pull of gravity shift with environment, reconciling galaxy regularities with cluster-scale demands. Not a conspiracy, just a network of settings that move together. The data keeps pressing. Baryon acoustic oscillations draw a precise ruler across cosmic time. Supernovae measure how bright that ruler looks at different epochs. Weak lensing maps how structure clumps and shears light. Strong lens time delays solve geometry with clocks. Each probe has its own systematics, its own quiet traps. Together, they squeeze the dark sector into a corner. The corner still has room. There's a human beat here too. A collaboration splits into two analysis teams with firewalls, each allowed to choose different cuts and calibrations. Then they meet to compare blind results. The numbers land close but not identical. The debate over which systematics to trust runs long. A junior researcher, staring at a lensing shear catalog at midnight, notices a subtle correlation with telescope-focused drift that shouldn't be there. They build a correction, and the S8 value slides by a hair. Enough to keep hope alive, not enough to claim victory. So where does the monster lead us? Maybe dark matter is a simple particle and dark energy a simple constant, and the cracks are our instrument fingerprints. Or maybe both heads are masks for deeper fields whose ripples show up as tensions, drifts, and anisotropies when our measurements get sharp enough. The stakes are simple to say and hard to solve. If the dark sector evolves, the constants we use to describe it might be evolving too. To test that, we need a yardstick deeper than galaxies and a snapshot older than starlight.